All right, so hello. This is a challenge problem from our thermochemistry workshop. The last problem in there, and I like this one because it is a doozy, but it also emphasizes and highlights really the entirety of the thermochemistry unit. So we have energy conservation ideas with calorimetry, we have phase change going on, we have reaction enthalpy going on, we have things changing temperature, we're finding the final temperature. So this is really the perfect storm of everything that we need to know. So let's just go through how I would approach this. So anytime I look at really any problem in chemistry, but particularly a thermochemistry problem, I want to know what is going on. What are the different steps that are going to happen in here? How does that relate to things changing? So what sequence of events? We might have to track several things at once. So let's just look at what we have here. And why don't we highlight some important information? So we have a coffee cup calorimeter. What are we told about the calorimeter? Calorimeter is 256 grams of water. At that, and we're told some mass of solid calcium chloride is added. And then we have ice initially at 5 degrees C. What's going to happen here? So if we kind of visually think about what happens here, we have our cup, right? Our coffee cup calorimeter that has water in it. I guess we can shade this, right? Inside that water. Well, I made it pink in the thing, right? We're going to have pink water. It doesn't say what color the water is, and the water's clear, so maybe we dyed it pink. We add to it this solid calcium chloride. Does it say what happens to the calcium chloride? Okay, so it's not explicit, but calcium chloride is a water-soluble salt, so it will dissolve into solution, just like if you added sodium chloride. And then we have our ice cubes, right? All right, terrible ice cubes. There we go. Beautiful. So what's going to happen? We can look at each of these. So our ice cubes start at minus 5 degrees Celsius, right? So our ice cubes, we want to think about what's going to happen to them. They're going to heat up. They're going to melt. And then they're going to heat up again, right? So if we think about those, what are these called? Heating curves. We have the energy added to something. We have the temperature. If we're looking at a substance, it'll heat up while it's in the solid phase. It'll melt. It'll heat up while it's in the liquid phase. It'll vaporize. It'll heat up while it's in the gas phase. So during these phase transitions, these only happen at specific temperatures. So in the case of water, that's going to be 100 degrees C and 0 degrees C. So our ice is going to go, we're going to have solid ice. It's going to go to 0 degrees C. It's going to melt. And then our 0 degrees C water, which is a liquid, is going to go to the final temperature that we don't know. So in this case, I am assuming these are going to end in the liquid phase. If it's not going to end in the liquid phase, you're going to get a temperature that exceeds the boiling point of water or the freezing point. So if that happens, if your TF is not possible because you can't have liquid water at that temperature, you're going to have to spice things up a little bit. You're going to assume everything goes to the phase change temperature, and then you're going to find out how much water undergoes the next phase change. So, but right now we're just going to assume that we end in the liquid phase, and that's usually reasonable for these water examples. So let's keep going. We have our calcium chloride. That's going to dissolve into solution. And we can look at what that heat of dissolution is up there. And we can see that that's exothermic. So we expect the temperature to go up. And then for our water, this is hard to say. So the water is going to change temperature. We do know the ice cube is going to make temperature go down. The calcium chloride is going to make temperature go up. So we don't really know offhand which direction this is going to go. It's probably safe to assume the ice cube will be way more impactful than 5 grams of salt, but who knows? So let's take this information now and let's parse it out a little bit. And by that, I mean, these are the phenomena we expect to see. So let's figure out for each of them how we can relate those to our kind of thermochemical principles. In other words, how do we describe these heat transfers, right? So let's start with our ice. So here, this is going to be the Q of our solid ice undergoing some kind of delta T, and that's going to be the mass of our ice times the specific heat of our ice times the delta T of our ice. So that's one piece. We have melting. Let's get a little more space here. Give me the Q of our solid to liquid. Oh, got a fat eraser there. Solid to liquid transition. And that's just going to be the amount of ice times the delta T of ice. And one thing I am going to be careful of is that notice that all of these values, or at least these two values, are per mole and this one's per gram. So I'm just going to use those as they pop up. So notice that this is the mass because we're given that in grams. This is the moles because we're given that in moles. And then lastly, we have, what's the color we haven't used yet? Orange. So we have the, so once this ice melts, let's redraw our cup. Deeper wall there. We have our initial amount of water on the bottom there, right? So that's undergoing some kind of temperature change. Fill this in. Those ice cubes that we put on top are going to melt. And as soon as that ice is melted, right, we're going to have a little itty bitty layer of water, the ice water, that's at 0 degrees Celsius. Right, so that water still has to go under the temperature change to go to TF. And that's sitting on top of our water down here that is at 26 degrees Celsius. And that's also going to go to TF, but they're going to go to the same TF because at thermal equilibrium, everything's the same temperature. So this right here, this is what students, or really anyone, even if I go ask my workshop leaders or my TAs or seniors, like this is the piece that gets left out. That after the water undergoes that phase change, it still has to get up to the final temperature. It's just not magically at the final temperature. So let's describe that. So here we have Q of the liquid ice. So that's still going to have the mass of the ice, but now it's going to have the specific heat of water. And the temperature change it's going to undergo is TF minus 0 degrees C, right? Because we're starting at 0. We just melted. So that's how we would describe our ice cubes there. Our calcium chloride, this one's a little more straightforward. This is a reaction, right? So we just have Q of, I'll label ClCl2, is going to be N delta H reaction. If we look up here, we kind of have that hint that the units for this are kilojoules per mole. So ultimately, I just need to find out how many moles of calcium chloride were dissolved and multiply it by that number. And that's how much energy that cost or gave up, provided, I guess. And then lastly, our water here. This is going to be just a Q delta T, right? We'll call this our calorimeter, I guess, just to keep it. I don't like that that looks like CaCl, but we'll leave it that way. So this is the mass of the water in the calorimeter times the specific heat of water times TF minus, and the initial temperature of this was 26, right? Minus 26 degrees C. So I probably should have called this TI since everything else here is variable. Let's just make that TI. So the last part of our theory here, these are all of the pieces, right? So we have what happens to our ice, what happens to our chloride, our calcium chloride, what happens to the water in our calorimeter. And now we just need to relate all of these. So we know that by conservation of energy, that I'm a big fan of all the Q's add up to 0. You can also do Q in is negative Q out. That does require you to decide kind of which of these are like which of these are endo versus exothermic, which is a good mental exercise. You know, the ice is losing energy, so that'll be positive, right? It's taking in energy from, I said that wrong. The ice is gaining energy. It's taking in energy from the environment. The calcium chloride is giving up energy. The water, we don't actually know which side of the equation to put it on. But the good news is that as long as you set these up correctly, like this is the same as writing this as Q in is equal, plus Q out is equal to 0. So as long as you write everything correctly inside this, it doesn't matter. So both get you to the end. I just think this one's a little easier to set up because we don't have to make decisions about where to put things, even if those decisions don't matter. But it'll save us some brain power that we can focus on other stuff. I was supposed to make this one orange. All right, so let's set this up. We'll just do a quick summary of our Q's. So the solid of our ice undergoing that temperature change plus the solid to liquid phase change plus our liquid ice undergoing the delta T plus our calcium chloride, and lastly our calorimeter all adds up. I'm going to have to move this whole thing over just so I can fit the 0 in. All adds up to 0, right? So now we just want to substitute in all of our numbers, right? And honestly, if you meticulously laid out all of this and this, you know, you've defined all of these, that's probably going to get you a lot of points in terms of how I assess things, because this is most of the work. Now it's just algebra substituting in. I guess I'm assuming that you know what each of these are, so if there are variable misassignments there, that could be a problem. But let's do it. So we have how much ice? 13.8 grams of ice. And this is going to be a very large equation, right? 13.8 grams of ice. Remember that specific heats are phase dependent. You know, if you have a solid versus a liquid versus a gas, you have different amounts of intermolecular forces in there, so you need different amounts of energy to break things up. So from there, we can see that the CP of ice is 2.05 joules per gram. And And we are going from negative 5.0 degrees C to 0 degrees Celsius. I wrote that backwards, didn't I? Because it's final minus initial, so we're ending at 0. And we are subtracting negative 5, right? So let's write it like that. So that's the Q of our ice. Now we want that phase transition. So remember, this is going to be the moles of ice. So we have to take our 13.8 grams to multiply that by, and divide it by the molar mass, I guess. So we have 1 mole per 18.02 grams. And then the enthalpy of fusion of water, 6.01 kilojoules per mole. And remember, fusion is specifically defined as melting stuff, so we don't need to worry about changing the sign. 6.01 kilojoules per mole. I do want to be careful at this point, so note that this is in joules, this is in kilojoules. I do need my units to match for this, so I either have to convert everything to kilojoules or I'm going to have to convert this to joules. I do think we're going to just pick up this whole thing and we're just going to move it down. So we're currently in kilojoules. I want, maybe I should move this mic down a little bit. There we go. I want 1,000 joules per kilojoule. There we go. Going to add in our ice changing temperature. So we have 13.8 grams. We should know the specific heat of water off the top of our head since we use it so much. And we don't know what the final temperature here is, but we do know that we're starting at 0.0 degrees Celsius, right? Now we're going to add in our calcium chloride. We're starting with 5.2 grams of that. If I was being really careful when I'm doing these conversions here, I would include the species. So like I would call it water earlier, or ice. And here I would call it calcium chloride just so I don't mix them up. But for the interest of space, I'm not going to worry about that. We are going to quick here off to the side Google the CaCl2 molar mass, which is 110.98. That's going to be a small number, which is not surprising. Calcium and chlorine are both large atoms. We need that enthalpy of fusion, so that's negative 81.3. 81.3 kilojoules per mole. And once again, we're going to include that conversion to make that into joules so that everything lines up nicely. And then at the very end, we have our calorimeter, right? So we have here 250.0 grams times 4.184 joules gram degrees Celsius times TF minus our initial temperature, 26.0 degrees C. There we go. And this whole thing is equal to 0, right? So now we have some options. If we're looking at this, let's see, what color can I use? I think this one will pop. So the only unknowns are these two final temperatures, right? The final temperature of the ice and the water coming together. If you forget this piece here, Notice that there's only 14 grams of ice compared to 250 grams of calorimeter water. So your answer will be close. Obviously, it'll be incomplete, and that's what matters. But it will be close. If there was a larger mass of ice here, this would become increasingly more important. But the heat capacity of the water is going to vastly outweigh that little contribution from the ice. All right, so how can we solve this? We have a couple ways. Again, if you're with my course, I do recommend using Wolfram Alpha. So why don't we see what that solution would look like? And you can use any symbolic math program here. See, it looks like we just go to .com. I'm going to toggle math input. Normally, I would use something called Maple, but Maple is not super accessible to students. It is free to you, but you have to remote into one of Delaware's remote computer labs, virtual computer labs, which is kind of annoying. So if we look at our problem here, this really isn't too bad in terms of like, we don't have to do any calculus. We don't have to do any differentials or anything. This is just algebra. We have multiplication, addition, and subtraction. So if we were solving this, we would want to like distribute across parentheses and stuff. I'll walk through that later. But because there are so many steps here and so many calculations, I wouldn't do this by hand just because it's so likely to result in an input error. All right, so let's shrink these so that we can see what we're doing here. I was kind of hoping that would like resize it. Oh, okay, it did. All right, so we'll just put this here and then we'll lower it so that my face isn't quite in the way. And I'm just going to type this in as I see it. Instead of TF, I am going to write T. I know that Wolfram doesn't like multi-letter variables by default. I'm sure there is something you can do about it. I wonder if we could take a picture of it and... Oh, you have to be pro. All right, so never mind. All right, so let's just go back to putting it in this way. So we're going to input these values here. So again, just typing these in, 13.8. You can put units in here. There is some way for Wolfram to recognize them, but I'm not super confident in how that works. And what kind of caveats are there. So I don't typically include my units. So do make sure that you kind of go through your thing here and double check that your units align. Because if you don't put units in here, Wolfram will calculate what your numbers say, but your numbers might not represent what the chemistry is. Alrighty. Times 2.05. I don't know if these multiplication signs, these asterisks, are necessary. And then we have 0 plus 5. 0 minus minus 5. I also don't know if Wolfram likes minus minus or not. So I know there's a lot of unknowns here. Times 1 over 18.02. Notice that Wolfram will like put in nice little fractions for you. You also have all these other options over here. So that's getting us our molarity of our ice times 6.01 times 1,000. All right, we're almost halfway there. I don't know why I'm writing all of these in parentheses. I don't need to. 184 times. So, okay, so here I'm just going to call this T. If I call it TF, it'll actually get mad at me. I do need my parentheses here, though, right? So, if you forget that parentheses, that's a calculation input error. That's going to mess up your result. 5.2 times 1 over 110.98 times, if it matters, negative 81.3 times that 1,000 plus 250 times 4.184 times T. And it's very important that this T and my earlier T are the same variable. So, if I want to call them X, I call them X, whatever. and then that is equal to 0. And we hit enter. So notice here that Wolfram does kind of do the initial simplification. It, multiplied all this stuff out. It expands it. So if you do all the crunching, you should end up with something that looks like this, and then you divide to get T. So that's one way. This is another way. It can approximate it by just finding out where roughly this line intersects 0. If you are using a graphing calculator and you're not allowed to use some kind of symbolic math software, you can totally put this entire line of text into like Y1 on your calculator, find where it intersects 0 using your calculator functions. So totally possible to symbolically solve that, even if you can't use Wolfram. Now, it's a huge pain, but really it's not that much different than typing it in here. All right, so that says that our final temperature would be 23.79, right? And why don't I write over these TFs in black so it's obvious where they pop up. 23.79. How many sig figs do I have here? This is where using Wolfram kind of hurts, in that if I were to do this by hand, I'd have an idea of where my uncertainty lies. I'm willing to bet that this right here determines my uncertainty. So 13.8 times 2.05 times 5. Will that get me 10, 130? Okay, so we're probably okay with using 3 sig figs. Well, it'll be a little clearer. So I would accept, because there are 3 sig figs given in the problem, that we're going to have a 3 sig fig answer. Whether or not the calculations support that's a different question. All right, so that's how I would go about solving this. I would do this symbolically with some kind of software to crunch the final number at the end. Another way you could approach this is you could set each of these Q's up as a value in Excel to kind of help you do some of that calculation there. And if you mess something up, you can just go back into your cells and change them. You still have to solve for TF somehow, though, and that Excel, I don't want to say it can't do it, but I'm not exactly sure how to do it. I'm willing to bet it can with some shenanigans. I bet there's a function for it, but I don't know off the top of my head. All right, so if we ignore our cheaty version of doing this, how else could we solve this? So obviously we would want to expand all of these terms. So let's see, this will end up being plus 5.0 degrees C. I'm going to take, right, I can just pull up the calculator here. So we have, why don't we put it so it's not on top of something? 13.8 times 2.05 times 5. This is hard to type on with my pen in my hand. So that gives us 141. I'm just going to round there. This is a 2 sig fig answer, so we have 141 joules. We're going to add, probably want to get some space here. And we could have done this up here too. Like when I write out each of these, I could just do it there rather than saving it all for the end. All right, we're going to have 13.8 divided by 18.02 times 6.01 times 1,000, not 100. So that's a big number, right? Did I math wrong? I did, yep. Divided by 18.02. And it's always good to check yourself as you're going through and be like, that doesn't feel right. Because that was way too much energy, like 9 megajoules, I think that was, right? That's not right. Or 9.9 megajoules, almost a megajoule. All right, so this is going to be 4600. Again, this is our sig fig here. Notice that I am keeping, I'm actually going to call that 4603. This is our sig fig. I am going to keep one extra sig fig after each of my things just to kind of mitigate rounding errors. Because if I round all of these to their sig figs in the middle of my calculation, I will miss my result a little bit. All right. So now things get a little complicated with this one, right? So when I multiply this out, I'm going to end up with 13.8 times 4.184. So this is going to look like 57.74 joules per degree Celsius. That's just combining these two terms first, right? So multiplying this together gives me this guy. I bet I could highlight that if I'm smart, right? So that's where that comes from. And then we have TF. Oh, this works out nicely. Minus 0, right? So when you have something like this, you have to distribute across that parentheses, right? So I would multiply this times TF, and I would subtract that times 0 from TF. Fortunately for us, 0 times something gives us 0. So we are just left with 57.74 joules per gram degree Celsius times TF. Now I'm going to make a new line here. We're going to do our green one. This will also be nice. Did I multiply wrong earlier? No, okay, we're okay. We're okay. All right, 13.8 divided by 18.02. Yeah. I was worried that I had mixed up my molar masses of CaCl2 and water just because talking and typing is hard. All right, so 5.2 divided by 110.98, that's our molar mass, times, I can't put a negative in here, so we'll have to negate it later, times 1,000, and then we'll just click that button. All right, so that's going to give us negative 3,809 joules, again with this sig fig here. I really thought these would be larger values, but I guess they cancel out. And now that we've calculated these values, we can see just from the enthalpy changes from the phase change versus the reaction enthalpy of dissolving the salt that the ice is a stronger effect. It contributes or it drains more energy from the system than the salt gives up. So we expect our solution to be colder than when we start, just from this step here. All right. And then lastly, we're going to do the same thing with pink here. We're going to multiply together this piece. That's going to give us 250 times 4.184. And this is actually the heat capacity of our calorimeter, right? So we're going to have, that's wrong. So our calorimeter, when we multiply these numbers together, we get 1,046 joules degrees Celsius per degree Celsius, right? And then that, again, we have to distribute that, right? So we're going to distribute that across our parentheses. So one of these is going to be times TF. And then we are going to subtract, this is going to be a number, so I think it'll fit, right? Because we have this negative here. So we're going to take this, we're going to multiply that by 26. We're going to lose 27,000. Well, lose is a strong word here. It's kind of like how much energy we're starting with. And then this whole thing is equal to 0, right? So now we can look at this and we can say, all right, so I have TF here and I have a whole bunch of constants. So why don't I add together all my constants, add together my TFs, and see what we're left with. Notice our TFs have the same unit in front of them, so we can combine those. So I'm going to take my 141, my 4603, I'm going to subtract my 3809, subtract my 27196 from that. All right, so I have negative 26261. And thank goodness that agrees with what's on Wolfram. And then we're going to add together our these guys, right? So you can tell from here that, again, we knew qualitatively that the heat capacity of the water, because there's 250 grams of it, was going to be much more impactful. So notice that basically 1,050 of our heat capacity comes from that, and the other 50 comes from TF. But we can add these together. I did not mean to say TF there, I meant from the ice. And that also agrees to the decimal with what Wolfram saw. So why don't we make this a fun color? Do blue, we have 1103. I'm just going to call it that. TF. Now we do want to look at these. And so it does work out that in all three of these cases, our sig fig, shoot, this one, nope, that's got 4. No, it's got 1 here. It's got 1 here, or 3 there, right? So 3 sig figs. So when we do our addition in our addition step, we are left with a sig fig here. So that has 3 sig figs on it. So that works out well for us, right? We wanted 3 sig figs. And then these ones, the heat capacities in front of TF here. Let's look at each of those. So this should have a sig fig there. We'll do that in orange, and this should have a sig fig there actually. But so when we add those together, these become limited at the ones place. So in this case, this is our sig fig. That's equal to 0. Now we just subtract from both sides. 1103 TF is equal to 261 with that 1 sig fig there. We will divide both sides by that 1103. I'm so sorry, guys. I forgot my units. All right, so we're going to put our joules here, right? Our joules here. Going to pull this over. We pulled over a little more than we bargained for. Pull. This has units of joules per degree Celsius. Same idea over here. Joules per degree Celsius, joules per degree Celsius. And this is important because when I do this cancellation here, you know, that cancels, this joule cancels, and I'm left with 1 over degree C in my denominator. So my final answer will have units degrees Celsius. Right, and then we go through, we divide that. I mean, we can 26261 divided by 1103, and that gives us, once again, 23.8 degrees C. So again, these match. Notice the sig figs are a little bit different. This said 23.79, or maybe not the sig fig. The uncertain digits aren't different. In this case, our last sig fig, which is technically the uncertain digit, is the same. But once we look past that, you know, we had 23.81 or 808 versus 7931. This little difference here is due entirely to me rounding in the middle of my problem. So as you do more calculations, the more rounding you do, the more and more those little rounding errors, we call them, add up. So that's kind of the ultimate calorimetry problem. Let's see, we are 40 minutes into me explaining how to do it. Without the explanation, this would probably still take me like 10 or 15 minutes. So this is obviously too much for an exam, right? If it takes me that long, I'm assuming it's going to take you guys 45 minutes. Usually about 3 times as long for you to solve it as me. But the pieces of it are fair game. So I could throw water into a cup and say, what's the final temperature? I could throw reactions into a cup or capture the heat from a reaction somehow and say, what's the final temperature? Fun stuff like that. So hope that helps us. But we can do it. We just got to take our time. Just go one piece at a time. And obviously it took me less time to type it into Wolfram than it did to do it all by hand, because you have to type it in somewhere anyways. So with that, I'm going to call it. So I hope that helps. I hope you feel a little bit better about how to do these calorimetry problems. I know you guys did want to see the numbers substituted in for the letters to get a more concrete idea. So hope that helps. And I'll see you guys in whatever our next video is. Okay. Blah. Look, it's just easier if I make loud sounds because they pop up in the audio waveform as these giant spikes and I can find them quickly scanning through the video.